Hello and welcome. My name is John Loaiza and this is my screencast presentation for my project called Creating a Self-Learning Scale Prototype of a Wheelchair Base to Facilitate Mobility for People with Physical Limitations. In this video, I will guide you through an explanation of the final design of the prototype, an explanation of the code implemented for the learning algorithm, and a series of test and learning sessions where the device was placed in a closed environment. In the end, a final test presenting the results and the learning of the prototype behavior will be presented. The final prototype implemented 5 sensors in the front of the device, in the shape of a semicurve. It was designed this way to provide a wide range area for the device to check for distances and to check for objects in the front. Starting from the bottom, to support the weight of the device, it was installed a tank-style base which had 2 powerful gear motors attached to it to power the movement. To control both motors separately, an L9110S driver was implemented. This one can be spotted at the back of the device. A Raspberry Pi computer was selected to act as the brain to implement the learning algorithm and to run the necessary code to check the distances and move the device. To avoid any soldering, a breadboard was implemented to serve as the intermediate connection between all the components, the sensor, the resistors, and the Raspberry Pi. To provide energy for the computer and the motors, 2 separate power supplies were implemented. For the computer, it was a power bank, and for the motors, 2 battery enclosures for 9V batteries. The next part of this explanation will be to guide you through the different files and functions that help to implement the learning algorithm for the device to learn by itself. The motors file is where all the functions for the mobility of the device are created. The way the functions are created is to first set the GPIO mode to GPIO board for the boarding numbers. Then we set the GPIO pins for outbound signals, and then we set the way these signals are sent in order to move the motor for a certain direction. Each action has a time frame. In this example, the action of going forward is set to be for a time of 0.8 seconds. After this action is completed, the GPIO setup will be cleaned up. The sensor file is the file that contains the function that allows to retrieve the distance from a single sensor. In this function, we are setting up the GPIO mode to board, setting off the warnings, and allowing a time frame of 0.1 seconds for the model to settle. After this, the trigger part of the sensor will be activated for 1 millisecond. The echo part will save the time when the signal is received and when the signal ends. Once this operation is completed, we can then calculate the total duration of the signal. With this, we can calculate the distance applied with the formula. The result is rounded to 2 decimal points, and then the GPIO mode is set up to clean up. In the state file, we can find the functions to check the distances of all 5 sensors, and based on this information, check the current state of the agent. The function to check the distances uses the ping function from the sensor file. This function is then looped within all the sensors, and the distances are saved within a list. To check the state, we first check the distances. With this information, we then implement an if statement to determine, depending on the distances, which state the agent is in, which reward it will take, and if the car crashes or not. Inside the action file, we see 2 functions for when the agent chooses to do a random action or when it chooses to do an action from the queue table. The queue learning file is where the queue learning algorithm is implemented. In here, we import all the other functions that we previously made. First, we initialize all the variables. First the action and the states for then create the queue table and initialize it with zeros, the maximum number of sessions, the maximum decisions per session, the learning rate, the discount rate, and set up the exploration rate, which the exploration rate decay. Also, we initialize a list that will contain the rewards from all sessions. Each session first starts with 10 seconds of waiting time. This allowed the user to place the device in the testing environment. The state is initialized to 0, the value of crash is initialized to false, and we create a current value for the rewards for the current session. Then, for each session, a maximum of 15 decisions will be made. Within each session, first the agent will decide whether explorate or exploitate the environment. After he decides how to make the action, then we will check the state. From the state we will get the new state, the reward, and if the car crashed. With this information, we can then update the queue table with the key pair of state action, set the current state to the new state, and save the current rewards for the current session. If the car crashed, then the session is broken and we pass to the next session. After a session is completed, then we update the exploration rate, add the amount of rewards from the session to the list of rewards from all sessions, and save the current queue table created. Once all sessions are completed, then we print out the average reward per 10 sessions and we print out the resulting queue table. For the final test, we implement the queue table that was saved from the learning sessions. The number of sessions this time is set to be 4, and per session, the maximum decisions are set to be 20. As this is the final test, the actions permitted for the agent are only the ones that he can retrieve from the queue table. From those actions, we can check then the state, get the new state, the reward, and if the car crashed or not. If the car crashed, we will print out a label, the session will be broken, else the car will be successful as it did not crash. With the queue table saved from the learning sessions, we can then use the information to create a heat map. In this heat map, we can see the key focus that the agent uses to make the decisions. Up next, you will see the test of the learning sessions. To complete all the learning sessions, the agent took more than an hour. Sometimes, giving the results that we were expecting. After the learning sessions concluded, some interesting results were discovered in the final test. We can see that the agent learned to go to the sides in order to avoid crashing. If we take a look at the queue table, we can then see that if the agent has a state of all clear front, it will tend to go to the right. Of course, by doing this, the agent will never crash and will always obtain a reward. Although the final behavior was not the expected, the agent actually learned from the queue table and the learning sessions. I hope you enjoyed this video and thank you for watching.